This is oscillations part 6. So in this video we will see, so first the two-body oscillator. What is a two-body oscillator? So suppose we have two blocks here. Okay, so M1 and M2 are connected by a single spring. Now initially the spring will have a natural length. Now what we do, we move both the blocks towards each other or away from each other. And the surface is smooth. So when you move both the blocks towards each other, and if you release, then both the blocks will oscillate with the same time period. Both the blocks will execute a session with the same time period. Even though the displacements are different, say the displacement of M2 is x2, the displacement of M1 is x1. Even though the displacements are different, so they execute a session with the same time period. So that same time period is called time period of two-body oscillator. Now this is called two-body oscillator. What is the time period of this two-body oscillator? So this is the time period of two-body oscillator. T is equal to 2 pi root over mu by k. Here mu is called a reduced mass. The formula for this reduced mass is this. This is the formula for reduced mass. Okay, m1 m2 by m1 m2 divided by m1 plus m2. This is the formula for reduced mass. So remember, children. Now here between these two blocks you can have any number of springs. Suppose we have a situation like this. Suppose we have block m1 here and block m2 here, and suppose two springs are connected like this. Now these two springs are in parallel, k1 k2. Now k effective is equal to k1 plus k2. That k effective we have to substitute here in the denominator. Suppose we have combination of springs like this. Suppose this is m1, okay, and this is k1, and this is another spring k2, and this is another spring k3, and so together they are connected to a block of mass m2 like this. So now k2 and k3 are in parallel, together they are in series with k1. So find the k effective value. That k effective value is substitute in the denominator. So this is regarding two-body oscillator. So now we go to simple pendulum. So we will see different cases of simple pendulum. But what is simple pendulum? So it consists of a thread or metallic rod or wire. Then so it consists of a spherical object called bob. Okay, the bob will have mass m. Now the time period of simple pendulum is 2 pi root over L by G. Here L will be measured. L will be measured from the point of suspension to the center of gravity of the bob. Remember, center of gravity, till the center of gravity. Generally, so you will misunderstand that L is the length of only the string. No, L is the distance between center of gravity of the bob and the point of suspension. Okay, so as you can see in the diagram, this is the main position, this is the extreme position, and this is another extreme position. Only for small amplitudes, it will execute a session. For larger amplitudes, it will not execute a session. It will become oscillation, but it will not become a session. So that's regarding the simple pendulum. We see simple pendulum in different cases. See here, simple pendulum with liquid leaking. What is liquid leaking? The bob or the spherical object is filled with a liquid, and we make a small hole here at the bottom. The liquid will be leaking. When the liquid is leaking, what will happen, children? The center of gravity of the bob decreases. The center of gravity of the bob lowers, so comes down. When the center of gravity of the bob lowers down or comes down, the length of the pendulum increases. The length of the pendulum increases. When the length of the pendulum increases, the time period increases. So once all the liquid is drained out, once all the liquid is leaked out, then the center of gravity comes back to the initial value, and now the time period will come back to the initial value. So remember, initially the center of gravity will come down, length increases, so time period increases, and again once all the liquid has been leaked out, so again the center of gravity will come to the initial position, and the time period also will become the original value. So we go to the next situation of simple pendulum. Suppose simple pendulum is suspended from the ceiling of a lift. The lift is accelerating upward with an acceleration a. So what is the time period? So if about this equilibrium position, if you slightly displace the pendulum and release it, it will execute SHM with this 2 pi root over L by G plus A. So here in such problems you have to find the effective G, children. How to find effective G? In equilibrium position you find the tension. So suppose if this person who is standing inside the lift applies Newton's laws. So it is a non-inertial frame of reference. In the non-inertial frame of reference, he has to take mg and ma. One pseudo force he has to consider. Tension T. So now tension T is equal to mg plus ma. So tension T is equal to m into g plus a. So tension T is equal to mg effective. In all such problems, in all these problems, you find the tension in the equilibrium position, equate the tension to mg effective. So m into g plus a. So now m will be cancelled here. You will get g effective is equal to g plus a when the lift is accelerating upward. So that g effective you have to substitute in the denominator here inside the root. So the formula will be 2 pi root over L by G effective. That G effective you have to substitute here. Okay. So suppose if the same lift is accelerating downward, then so it will be G effective will be G minus A. Suppose if the lift is freely if the lift is freely falling, so if the lift is freely falling, if the lift is freely falling, then A will be equal to G. When A equal to G, time period will become so infinity, which means that the pendulum will not oscillate. The pendulum will not oscillate when A equal to G downward. Then suppose the pendulum is suspended from the ceiling of an accelerating car, accelerating bus. Suppose the bus is accelerating horizontally. Then in equilibrium position, the pendulum makes an angle theta with the vertical. That angle is given by tan theta equal to A by G. Remember this. This is the angle. Now about this equilibrium line, if you slightly displace the pendulum and release it, it will execute SHM for small amplitudes. So now what is the time period of that SHM? This is the time period of that SHM. So here G effective will be equal to, so root over G square plus A square. This is the G effective. How we get that? Already I told you the logic. In equilibrium position, find the tension. So here there will be mg and there will be ma. If a is the acceleration, so right word. Okay, now so tension T is equal to root over mg whole square plus ma whole square. Now T is equal to mg effective substitute. M you can take common inside the root from the root and you will get this as G effective. Once you get delta G effective, now substitute in this formula. T is equal to 2 pi root over L by G effective. So this is how you get this formula. So now next situation. Suppose the pendulum is suspended inside the liquid and it is made to oscillate. Now instead of taking mg, so you have to take apparent weight. Mg minus force of buoyancy is apparent weight. So now mg effective will be equal to mg minus so force of buoyancy. That is, so I'll write here. So now mg effective is equal to mg minus force of buoyancy. This is apparent weight. That is mg minus force of buoyancy is volume of the bob, volume of the solid submerged into density of the liquid into G. So now mg effective is equal to mg, but we here in place of volume we can write mass of the bob divided by density of the bob into density of the liquid into G. So here in place of mass volume of the bob we can write mass of the bob divided by density of the bob. Now m you can take common and you can cancel and you will get G effective as G minus rho L divided by rho B. So here I'll write, so G effective as, so G you can take common here, G you can take common here. So once if we take G common, so 1 minus rho L divided by rho B. So this is what you get, children, G effective. Okay, so that G effective is substitute in this formula, 2 pi root over L by G effective, you will get this as time period. So once again have a look into that formula. What is G effective? and what is time period. Here rho L is density of liquid, rho L is density of liquid, and rho B is density of the bulb. Rho B is density of the bulb. Okay. So now suppose if the same simple pendulum is suspended in the electric field. Suppose we have a horizontal electric field. Then the pendulum will be deflected rightward if it has positive charge. Then about this equilibrium line, if you oscillate, if you pull it away and release it, it will execute a session. What the time period? So this is the time period. G effective will be root over G square plus EQ by M whole square, and that G effective value is substituted here. Here also in the equilibrium position, find the tension T. So tension T to find. So to find the tension T, you require mg and electrostatic force. Okay, so here mg effective, tension is nothing but mg effective is equal to root over mg whole square plus so EQ whole square. Okay, so now calculate G effective value, you will get that G effective value like this. So that's all children in this video. Thank you.